Okay, we're starting Chapter 2, and Section 2.1 is Rates of Change and Limits. So we've talked about this a little bit already, average and instantaneous speed. A body's average speed during an interval of time is found by dividing the distance covered by the lapsed time. So speed is a specific form of slope. If I have distance and time, and I take a trip, I'm traveling a certain distance, and I go a little slower, and then I speed up again. Any place on the graph, if I go from here to here, would be the change of distance over the change of time. In other words, y minus y over x minus x. So that's a slope or an average rate of change. So we're going to use a specific example of this. A dense object dropped from rest to fall freely near the surface of the Earth will fall at 16 t squared feet in the first t seconds. So if I want to find an average speed, let me see what I want to do here. No, let's do this. An average speed from t equals 0 to t equals 2, in other words, in the first 2 seconds, I'm going to take, using my equation for falling, I'm going to take that the average speed is 16 times 2 squared, that's my y sub 2, minus my y sub 1 over x minus x. And if I figure this out, I get 32 feet per second. So in the first 2 seconds, this object drops at a rate of 32 feet per second for average. So this is my average velocity for t equals 0 to t equals 2. So that's great. We can do that anytime we want. That's slopes. We did it in Algebra 1. But what if I want to find the instantaneous rate of speed at t equals 2? Well, instantaneous means 1 point. And I can't really do f of 2 minus f of 2 over 2 minus 2 because I just get 0 over 0. So let's do this. Let's say that h is a really small number. And I'm going to do f of 2 plus h minus f of 2 over 2 plus h minus 2. So putting this into my function, this is 16 times 2 plus h squared minus 16 times 2 squared over, this just simplifies to h. So let's expand this and see what we get. I get 16 times, remember I have to FOIL this, 4 plus 4h plus h squared minus 64 over h, which comes out to 64 plus 64, what did I do wrong? No, that's right, plus 64h plus 16h squared minus 64, and these cancel as well, and I can simplify by dividing everything by h. So here's an equation for my almost instantaneous rate of change at t equals 2. If I am moving from t equals 2 to some number that is 2 plus h when h is really, really small, it's still not quite instantaneous rate of change. But if h is 0, which I now can do, so at t equals 2, when the change on the x-axis is 0, I find that 64 is the answer of how many feet per second as my instantaneous rate of change at t equals 2. So the average from 0 to 2, and remember at t equals 0, I have no speed. At t equals 2 exactly, the rock is falling at 64 feet per second. So this is a way that we can use to find instantaneous rate of speed. Even though I can't find the slope at one point, I can't do it this way. I can, using this little plus h, sometimes I can get an answer at the end. All right, so this really has to do with limits. What we're saying is that we want to take the limit of this function as h approaches 0. So let's back up now and look at limits. The average speed, or average rate of change, of a moving body during an interval of time is found by dividing the change in distance, delta t, over change in time. You don't have to write that all out. This is our average speed, is delta d over delta t, and that's simply a slope value. The speed of a falling rock is always increasing. If we know the position as a function of time, we can calculate the average speed over any given interval. But we also can talk about instantaneous speed or instantaneous rate of change. We can do this over the next example as we use the idea of a limit to make precise calculations for rate of change. All right, so a limit. Let C and L be real numbers. And I'm going to draw a picture of this because I think it will make more sense. This is my x-axis. This is my y, or my f of x axis, my function value. So if C is some value on the x-axis and L is some value on the y-axis, the function f has a limit L as x approaches C. Now write this down and then we will talk about it. All right, so I have a function that is doing something like this, and as we get closer and closer to C, moving along the x-axis, we get closer and closer to L. So this is my function f of x. The limit of this function as x approaches C, as we get closer to C from either direction, is L. That's what this is saying. If I take the difference between any x value in C, and it is always between 0 and some value delta, that's a lowercase delta, then the function value is always going to be very close to the limit, and this is epsilon. And what we're saying here is that delta and epsilon are really, really little numbers. So as I get very close to C, squeezing in here, my function value becomes closer and closer to L. So everything is squishing in there as I get closer and closer, and I can say that there is this number L that is the limit as the function approaches C. So let's look at what this means for us for limits. The sentence that is stated like this is read, the limit of f, or you can say f of x, as x approaches C equals L. The notation means that the values of f of x of the function f approach or equal L, and this is important, or equal, they don't have to equal it, as the values of x approach but do not equal C. So we're going to look at an illustration that will help us with this, but get this sentence down and some of this information. All right, so let's look at these pictures. So this is the same function with a little bit of difference. In this function we have a hole. In this function we have a hole, but we have a function value somewhere else. It's a piecewise function. And in this function we have a line that is solid with no breaks. So this function has a limit of 2. The limit as x approaches 1 of f of x equals 2. Even though there's no value there, as I get closer and closer to 1, but not quite there. My function gets closer and closer to 2. So as my delta becomes really little down here, 1 plus or minus delta, the change, my epsilon up here also becomes very small. The delta is the difference between the 1 and the x value, and the epsilon is the difference between 2 and the function value. Now we're going to say the same thing here. Even though the function drops down to 1 at x equals 1, we are still going to say that the limit as x approaches 1, not is 1, doesn't equal 1, but approaches 1, of the function is still 2. The limit is still 2. Even though the function value is 1, as we approach 1, we have a limit of 2, because we get close to 2 this way, close to 2 this way, but even though we never get there, that is still our limit. This is the one that makes the most sense. The limit as x approaches 1 of f of x here is 2, and when we put in x equals 1, we actually get the value 2. So even if it's not defined, or if it is defined but the function value is not where the limit exists, we can still find limits of all these functions. So let's look at some properties, and then we're going to go back and look at another example of how we can find our limits. If L, M, C, and K are real numbers, and if we have two scenarios, the limit of the function f of x as x approaches c is L. So we have a function at a certain point that has a limit of L. We have a different function that at a point C, the same point is a different limit M. We have some rules. The sum rule. The limit of the sum of the functions is the sum of their limits. And you do need to get some of this down so we can work with it. The difference rule. The limit of the difference of two functions is the difference of their limits. So what we're saying here is that we can add or subtract the functions first and then figure out what their limit is, or we can just find the limit of each one separately and add or subtract those limits. You're going to have to pause to write because I am going to keep going here. The product rule, this should be a multiplication, not a box. It didn't come through right. So if I multiply two functions together, their limit is the product of their limits. If I multiply a function by a constant k, then I can multiply the limit by the same constant. If I divide two functions, their limit is the quotient of the functions. So again, pause and write those rules down. The power rule, if I take a limit of a function raised to a power, it is the limit raised to the power. And a few other quick properties. A constant is always, the limit is always itself. And if we are using the function x, in other words, y equals x, then the limit of the function is always the x value. In other words, y and x are the same. And I can go over these in class if anything is not quite clear. I know it's a lot of content today. Okay, so let's look at these different examples of finding a limit. So this is a sum of three limits. I can find the limit of each one individually and then add them together. So the limit of 3x squared as x approaches c, and the limit of 2x as x approaches c minus the limit of 9. So I'm going to plug in c for x, and I know that this looks just like what we started with, and that really is what the case is here with a polynomial. This function has no holes. It's a straight polynomial function, does something like this. So if I can find the limit at each place and add them up, I will get the limit of the whole function. And we could do that with a number. So let's say we want the limit as x approaches 1. Is the limit as x approaches 1 of 3x cubed plus the limit as x approaches 1 of 2x, plus the limit as x approaches 1 of negative 9. I should have said minus and use a plus 9. That would make more sense. So plugging in 1, I get 3 plus 2 minus 9, and the limit is negative 4, which is the value of this function when x equals 1. Polynomials and rational functions. The function of any polynomial function, then the limit is simply plugging the number in. If we have a rational function, provided that g of c does not equal 0, the limit is just what you get when you plug in the value for c. All right, so let's do another limit here. All I have to do is plug in my 5. This is a polynomial function. So I'm going to just plug in 5. Doing the math. Continuing, I get 96. So the limit, oops, let me back up. I always like to write it again. The limit as x gets close to 5 of this polynomial function is simply the value of the function. So with polynomials, limits of many familiar functions can be found, or as with polynomials, limits of a lot of functions can be found by simply substituting at the points where they are defined. So trig functions, which are continuous, they don't have any breaks or holes, exponential and log functions, and composites can all be done by just substituting in the value that you want to find a particular limit. We'll be doing plenty of these to get practice. So here's another example. So if we look at it graphically, this is what this function looks like. And as x approaches 0, in other words, as we're getting close to 0, both sides coming in, it looks like we should have a function value there. And it looks like it's going to be at 1. So graphically, when we look at this graph, it seems like the limit should equal 1. Let's use it algebraically. So plugging in 1 and doing my quotient of my limits, and then, plugging in 0, 1 plus sine 0 is 1 plus 0, and cos 0 is 1, and we do in fact get 1 again for our answer. So looking at a graph, we can see a limit. Analytically, by plugging in the number, we can find a limit. Now remember, this only works if we can plug the number in and we can get a real value. Let's look at another one. Graphically, it looks graphically that as we approach 0, as we come in close to this, it looks like there is no limit. As I come from this side, I'm going way down. As I'm getting close to 0 from this side, I'm going way up. So it looks like there is no limit. Analytically, we can't use substitution because when x is replaced by 0, the denominator becomes 0 and the function is undefined. So what we're saying here is if there is a vertical asymptote, there is no limit at that particular point. Okay, last topic here. I know this is getting long, but we are going to plow through this. Sometimes the values of a function f tend to different limits as x approaches a number from opposite sides. When this happens, we call the limit of f as x approaches c from the right-hand limit, and the limit as x approaches c from the left as the left-hand limit. And we write it this way. So as x approaches c from the right, we can find a limit, and as x approaches c from the left, from the negative side of the graph, we can also find a limit. Now they may not equal each other. We sometimes call the limit as x approaches c the two-sided limit to distinguish it from one-sided right-hand and left-hand limits. A function f of x has a limit if and only if the right-hand and left-hand limits at C both exist and if they equal each other. So write this down and we will work on this together. The limit as x approaches C of f of x equals L. Only if and only if, that's what this means, the limit as x approaches C from the right of f of x is L, and the limit as x approaches C from the left is L. Now let's look at some things and tie this together. So here is a graph, and we want to find some limits from the given graph. So let's look for the limit and draw this diagram on your paper as x approaches 0 from the right of this function. So coming from the positive side, from the right towards 0, it looks like this graph comes down and gets closer and closer to 0. So as I approach from the right, and that means I'm going in a left direction, be careful of that. Now, this should equal 0, because as I come from the right, as I go towards 0 from the right, going in this direction, I'm approaching a function value of 0. Let's look at the limit as x approaches 2 from the right. So again, coming from the right-hand side, but getting closer and closer to 2, as I do that, the function gets closer and closer to 4. So my limit is 4. Remember, this is my x value, this is my function value or my y. So as I come towards 2 from the left, I get close. Oh, no, I don't. Let me back up. As I come from the left, my function is coming this way, and it's approaching nothing. There is no function value in here. So this one, I'm sorry, I was looking from the left, does not exist. DNE, does not exist. All right, now let's look at the limit as x approaches 2 from the left. Now, as I come from the negative side and I'm getting closer to 2, the function is getting closer to 4. Let's try 2 more. Let's see if I can get them right. The limit as x approaches 2 of f of x. You notice there's no sign here. That means if I'm getting closer to 2 from the left and from the right, I am not approaching any particular number. From the left, it's way up at 4. From the right, there's nothing there at all. So this again does not exist. Let's look at one more. The limit as x approaches 3 from the right of the function f of x. So again, as I come from the right towards 3, I am approaching 0. We will do some more practice on this, and I know there was a lot in this video. The squeeze theorem, we're going to, actually we're not going to look at it at all right today. We aren't going to use this too much in Calc AB. When and if we come to this topic later on, we will circle back for this. So don't worry about the squeeze theorem. And that's it. Sorry it was so long, but I think we're done for the day.